All right, guys, welcome back. We're going to continue our discussion about DMVPN in this topic here. I actually went ahead and kind of combined a few different lessons together, so we'll be able to knock out a couple of these concepts with DMVPN Phase 2. In our previous lessons, we've already covered all of these DMVPN topics. And honestly, there's really not much to DMVPN Phase 2 configuration, other than maybe some of the considerations about the next hop preservation and some of the restrictions when we're dealing with specific routing protocols. So that's what we're going to be covering in this lesson today, which is DMVPN Phase 2. And then most likely we're going to obviously have to cover DMVPN Phase 3, but I wanted to cover that as a separate topic. Hopefully we'll be able to cover that on Wednesday, maybe tomorrow. It will be probably about a 45-minute discussion. So it's not too long, but let's go ahead and get started. We're going to use the same topology that we've been using over the last few lessons, but basically we're just going to see how, in this particular case, DMVPN Phase 2, the configuration is not really much different, but we're going to see how it changes the traffic patterns of the hub and the spoke environment, and how this changes the design, not really from an overlay perspective, a DMVPN perspective, but more of how does this change the design from a routing point of view. And we'll take a look at DMVPN Phase 2 with RIP, with EIGRP, with OSPF, BGP, and talk about some of the restrictions, some of the requirements, a couple of additional configuration pieces that we have to consider as well when we're implementing specifically like BGP or EIGRP, and OSPF always, as usual, is going to be much more difficult and less applicable in this type of design because of its hierarchy, right? EIGRP, RIP, BGP, they all have arbitrary hierarchies and work pretty well in just about any DMVPN environment. But with OSPF, with the spine leaf or the leaf spine leaf design, we have to enforce the hierarchy. All right. So before we get into some of the specifics in the implementation, I want to do kind of a quick review of some of the differences between DMVPN Phase 1 and DMVPN Phase 2. And so here's our notes from the last discussion that we had, last few discussions we've had about DMVPN. One of the most notable differences with Phase 1 and Phase 2 is that we're running multi-point GRE on the hub, but we're also going to be running multi-point GRE on the spoke routers as well. So we're going to have to make a minor configuration change on our spoke routers to facilitate spoke-to-spoke communication. But we do not have, in the case of DMVPN Phase 3, we have the ability to do an NHRP redirect. We don't have that capability in DMVPN Phase 2. So as far as network reachability and network layer reachability information, we do have some specific design requirements that we're required to follow with regard to DMVPN Phase 2. All right. The NHRP protocol is still going to be required, of course. We're still going to use NHRP for spoke registration to the hub. We're also going to require NHRP for spoke-to-spoke resolution, but it has to be direct spoke-to-spoke resolution. There is no proxy ARP functionality, if you will, or redirect functionality that we have on the hub, which is what we'll see when we get into DMVPN Phase 3. All right, the spoke-to-spoke tunnels do get triggered by the spokes themselves. They're not triggered by the hub. So that's a distinct difference between Phase 2 and Phase 3. And so routing is a big consideration. Unlike DMVPN Phase 1 and DMVPN Phase 3, where summarization, default routing, and whatnot is supported on the hub, in DMVPN Phase 2, not supported. All right? So we have to make sure that we preserve the next hop and so on. All right? The design itself, from a scalability standpoint, is hard to scale. And that's because the next hop does have to be preserved by the hub to trigger the correct resolution in NHRP. All right. Now, if you only have maybe 10 spokes or 5 spokes or whatever, and you're only talking about a few prefixes, that's not a big deal. But if you have 10,000 nodes or 10,000 routes, obviously that's going to be pretty significant, because now we don't have any way of providing any kind of minimization of the routing information because of the preservation requirement that we have with DMVPN Phase 2. The next hop on the spokes always has to be preserved by the hub. That means to say that if spoke A is advertising a network prefix to the hub router, the hub router is then going to repropagate that network prefix to the other spokes. The next hop has to be the spoke that originated that route, not the hub. In the case of DMVPN Phase 1, it doesn't matter if it's the hub, because we don't have any spoke-to-spoke communication. And in DMVPN Phase 3, it also doesn't matter if it's the hub, because once we sent that initial packet to the hub is then going to identify that there's a better routing plane for the data plane. There's a better path for the data plane. And it will then in turn identify to the other spoke how the data plane should be switched, okay? We'll see that when we get into the Phase 3 configuration. All right, it's very difficult in Phase 2 to create a hierarchy. Ultimately, the solution is, especially if you require spoke-to-spoke communication, is to simply run DMVPN Phase 3. And there's only a couple of commands that differ between Phase 2 and Phase 3. So in most cases, this is somewhat considered to be obsolete, just like Phase 1, but we still need to understand the implications from a routing perspective of running DMVPN Phase 2 and so on. All right, so let's start by reviewing the configuration on our hub router. Not every line, because we don't really need to take a look at every element of configuration, but let's go back into our hub router and just do a show run interface tunnel 0. All right, now the key element here is this command right here, tunnel mode GRE multipoint. That's what identifies that this is a DMVPN, well, potentially a DMVPN Phase 2 configuration. In every case, Phase 1, Phase 2, or Phase 3, the hub is always going to have GRE multipoint. But if I go and look at one of the spoke routers, we can see that in this case we don't have the GRE multipoint configuration. We have a specific tunnel source and a tunnel destination specified, which means that this has to be DMVPN Phase 2. It's the only DMVPN phase where we specify the actual tunnel source and tunnel destination. All right. All right. So we're going to modify that configuration. That's going to be part of the change that we're going to have to make. The tunnel destination really defines that we're actually using DMVPN Phase 1. So in Phase 2 and Phase 3, because spoke-to-spoke communication is allowed, we need to convert the spoke tunnel interfaces to multipoint. All right. Now, if we're going to be running OSPF as a routing protocol over this DMVPN network, we only have 2 topology choices that are allowed, and there's still some restrictions on which router can be the DR, which routers can be the BDR in these particular topologies. In OSPF, we have 5 network types, right? We have broadcast, non-broadcast, point-to-point, point-to-multipoint, and point-to-multipoint non-broadcast. All right, and each one of those network types has a specific, specific set of, what's the word I'm looking for? I don't know why I lost my train of thought. They operate in a specific way, right? With regard to whether or not there's a DR-BDR election, whether or not automatic neighbor discovery is going to be permitted, and so on. So those design considerations are definitely something that we have to take into account. And we can play around with this and take a look at some of the different implications of implementing these different protocols. And that would actually be my suggestion. Familiarize yourself with what's necessary for each of these protocols to run from a design perspective. Obviously with the distance vector protocols, BGP, we're going to take a look at a configuration of BGP that I think is going to be fairly new for you guys. And that'll be kind of an introduction to what we're going to be talking about in BGP, which we're going to be getting into in the next couple of weeks. All right. We could do, for the purposes of DMVPN Phase 1 or Phase 2, we could do broadcast, of course, still having to control which router is going to be the DR, which routers are going to be the BDRs, or we could do point-to-multipoint. We could do non-broadcast or point-to-multipoint non-broadcast, but that kind of defeats the whole purpose of using DMVPN, because we would have to eventually configure all of our spokes and our hub manually, because automatic neighbor discovery wouldn't be allowed. And, that kind of defeats the whole purpose of the dynamic discovery process. All right, so let's start by turning off all the existing routing that we already have in place. Then we're going to go ahead and add OSPF to all the routers before we can convert to Phase 2. Now, another component of this is that all of the interfaces need to be placed in Area 0. All right, and we'll talk about why that is as part of a design consideration with DMVPN. But let's start by just doing a quick show IP protocols. I believe we left off running RIP. Yep, we're running RIP. And show IP protocols, and we're running RIP here. We could potentially just enable OSPF on top if we wanted to, because OSPF has a lower administrative distance than RIP. But let's go ahead and make it clean, make sure that we get rid of all of our stuff. All right, so let's go ahead and just disable RIP, config T, no router RIP. All right. And since we're going to go ahead and enable OSPF on all these networks, I'm just going to do a router OSPF 1, and we're going to do a network of 10. We want to make sure that we're enabling OSPF on the loopback interfaces and also on the overlay network, the 10.10.10 overlay network. All right. So let's do, back to my GNS3. Sorry, my PuTTY. Config T, no router RIP, and router OSPF 1, network 192.168. Let's just do 0.0, 0.0.255, 255 area 0. So those will be the loopbacks that are simulating our layer 3 routed network. And then we're going to go ahead and enable OSPF on the overlay as well in area 0, and we'll just save that configuration. All right, so we should be able to form adjacencies. We want to make sure that everything is kind of working before we decide to switch over to DMVPN Phase 2. So let's go ahead and confirm that we have adjacencies on each of the routers. R5 actually really should be the only one that's going to have adjacencies. We don't have any as of yet. Show run pipe section router. Make sure I didn't mess something up here. Well, that didn't work. What the heck? Show run pipe section router. For some reason it didn't apply the configuration to router 5. So let's go in here, no router RIP, router OSPF 1, and network 10.10.10.0, 0.0.0.255 area 0, and network 192.168, 0.0, 255 area 0. All right, so now we should get our adjacencies. And we need to talk a little bit about, how these adjacencies work in DMVPN Phase 1. Remember, all the traffic in DMVPN Phase 1 needs to pass through the hub. All right, so if I do a show IP OSPF interface tunnel 0, I should see, this might be a bit of a problem. I should see tunnel is up, the line protocol is down. Ah, I know what the problem is. I keep forgetting that every time I restart these, not that one, every time I restart these routers with IOSV, you have to do a no shut on your physical interfaces. So let's do that. All right, there we go. Now we're starting to see some adjacencies. Show IP OSPF interface, tunnel 0. All right. Now, I expected this to happen, and I brought this up for a specific reason. And here's the reason why. Okay. By default, OSPF is going, let me do this, no logging console. Oops, no logging console. Oh my gosh, no logging console. Try this one more time. Buffer's getting a little full here. This behavior that you're seeing here is actually is because of a very specific problem, right? OSPF is trying to form an adjacency with the peers, the spoke routers. And what's happening is that as each spoke comes up and talks to the hub, it's basically saying, hey, I want to be a neighbor on this link. But if I do a show IP OSPF interface, tunnel 0, I can see from this particular case that OSPF is treating this tunnel interface as though it's point-to-point. And by definition, a point-to-point interface is only allowed to have one adjacency. Now, there's a couple ways we can fix this. We can change the, to stop this churning, if you will, where the hub can't form an adjacency with all the peers. I can change the network type on the interface. So I can come into interface tunnel 0, and I can say IP OSPF network point to multi-point. All right. Now what that should allow is multiple adjacencies to form between the peers. Let's do a logging console and do a show IP OSPF neighbor. And nope, we don't have any adjacencies yet, but there's probably another reason. Let me check one more thing. Show IP OSPF interface tunnel 0. Yeah, so this is another issue, right? We've changed the network type to point to multi-point, but point to multi-point is going to have a different set of timers, show IP OSPF interface tunnel 0, than point to point. Point to point interfaces have a hello timer of 10 seconds, a dead timer of 40 seconds. So remember, we're still running DMVPN Phase 1, which means that the hub needs to form adjacencies with the spokes. We're not doing a DR-BDR election because if the network type is point to anything, there is no DR-BDR election. So point to multi-point, point to point, point to multi-point non-broadcast, there is no DR-BDR election. But we still get automatic neighbor discovery because we're not running a non-broadcast mode. Any of the non-broadcast modes, like point to multi-point non-broadcast or non-broadcast or NBMA, those are going to be where we don't have automatic neighbor discovery. So what I have to do now is I have to go into the interface and I have to say IP OSPF hello interval 10 seconds. So do show IP OSPF interface tunnel 0, and we can see that we're obviously getting our adjacencies with our peers, and on top of that, we've got our timers adjusted. So again, these are the kinds of things that you need to consider when you're using this type of DMVPN topology, because the concepts of OSPF that we learned in all of our OSPF discussions still apply. You still have to understand the implications of topology design, the leaf spine leaf design. We don't have to worry about that in this case because we're running a flat topology. But you need to understand the implications of that as well, right? For example, if there's a change on a spoke, it's going to propagate through the entire failure domain, which is area 0 in this particular case. All right? So in the OSPF graph, OSPF treats the tunnel as a point-to-point by itself, including the hub. All right? So the process of this churning over and over again is basically because the hub cannot form an adjacency with all the spokes. It forms an adjacency with one spoke, or it tries to go through the process of forming an adjacency with one spoke, and then it hears from another spoke. So it's going to now it'll ignore the first one, and now it's going to try and form an adjacency with another spoke and so on. All right. Now, if I would have gone to all of the interfaces, all of the routers, and said IP OSPF network point to multipoint, I wouldn't have had to worry about adjusting the timers. But there's really no reason in establishing the spoke routers as point to multipoint with a DMVPN Phase 1, because they're only going to be communicating with the hub anyway. All right. Another thing that I want to mention here, let's leave it the way it is right now, but another thing that I want to mention here is the cost of a tunnel interface. We're establishing this tunnel over a gigabit Ethernet connection, which means it really should have a cost of 1 based on the interface that it's tied to using the default reference bandwidth. Man, I don't know why my mind is fried today. I don't know what's going on. But we got the default reference bandwidth, which is 10 to the power of 8, which means that we're going to have a cost of 1. But artificially, tunnel interfaces the bandwidth is artificially set to a low value. So if I do a show interface tunnel 0, you can see that the bandwidth of the interface is set, show interface tunnel 0. You can see that the bandwidth of the interface is set to a relatively low value, 100 kilobits per second, which is why, and the delay consequently is also set to a very high value, 50,000 microseconds. So this would obviously have a pretty vast effect on EIGRP as well. All right. But the idea here is that we've artificially set this value to a pretty low value, which means proportionally the cost is going to go up significantly. All right. On the spokes, it doesn't really make sense that we would want to get all the routes from all the networks with DMVPN Phase 1, because in reality, the spokes just need to send their traffic to the hub. We talked about that concept in one of our previous lessons. All of the network is a flat area 0, so we can't do any summarization. It wouldn't be allowed in DMVPN Phase 2 anyway, because we're only allowed to summarize on area border routers. All the spokes are part of the same area. They can't have a different view of the OSPF graph. We could do something like route filtering, where we could filter out routes from the rib. And, they would still go into the fib, but we could kind of filter out some of those routes based on injecting a default route. So for example, if I come into router 1 right now, we won't have too many routes, but show IP route, OSPF. I can see that I have 4 OSPF routes. Now, extrapolate this, of course, to maybe thousands of routes or tens of thousands of routes in a very large DMVPN environment. I don't have the capability of summarizing these networks or summarizing these prefixes. So my only option then would be to inject some sort of default route. So I could come into here and my hub router, and I could say default information originate. Why am I not, default dash information, sorry. Information originate. I'm going to go ahead and do it always since I don't actually have a default route on router 5. So now I am sending in a default route, and what I should see on these routers now is the default route. What I could do then is I could suppress these routes by applying some sort of distribute list filter. So if I came into router 5, for example, and I said IP access list standard filter OSPF, and I said permit 0.0.0.0, 0.0.0.0.0, and then I went back to router OSPF 1 and just did a distribute list, and we're going to send this into, well, let's do out. I think out might work. Distribute list. I might have to do this on the spokes, but let me see if it'll work here. Out. I should see some of those other prefixes get filtered out. I might have to apply the filter inbound on the spokes themselves. Just trying to think of permit filter OSPF. Let me do a clear IP OSPF process. Yeah, we're still getting the prefixes. So let me try this. IP access dash list standard filter in OSPF and router OSPF 1. Oops, that's not going to work. Permit 0.0.0.0, 0.0.0.0. Could do this with a prefix list as well. Router OSPF 1. Distribute list filter in OSPF. Oops. Control E in. Let's see if that works. There we go. Yeah, I was thinking I'd have to apply it on the spoke. There's probably a way to get it to work on the hub for whatever the hub sends out to its peers, but certainly it works on the inbound. So now we're basically suppressing all of the detailed prefixes. But here's the thing, that's our routing information base. If I do a show IP OSPF database, we can see that we're still getting the type 1 LSAs. So we're still building the graph. We're still identifying the individual links that exist. But as far as what's going into the routing information base, that's filtered based on our distribute list filter that we applied to the spoke. All right. So it doesn't affect the database, but it does affect the types of routes that we're leaking from the database. And in this case, we're only leaking out of that database the default route. That makes our routing table a little bit smaller, a little bit more manageable. Okay. There's other ways to do it, of course. We could apply, prefix list filtering. We could do other types of filtering, but what we can't do is we can't do any kind of type 3 LSA summarizations or anything like that because we only have a single area. So we're not allowed to create those summaries. All right. We're in this sense, from the overlays perspective, we don't know really what the topology looks like. We're hiding the details of the underlying topology from the routers. But if we make a change to that topology, yes, the OSPF link state information is going to get propagated, but ultimately our routing table and our routing information base is going to remain the same. All right. Now, what we want to do next is we want to go ahead and convert this topology to point to multipoint. All right. And let's find out what's necessary in order to do that, basically moving from DMVPN Phase 1 to DMVPN Phase 2. So if I go show run interface tunnel 0, I can see that we have a tunnel destination specified here and a tunnel source. If I look at my hub configuration, do show run interface tunnel 0, I only have a tunnel source specified, and then I have a tunnel mode specified. That's essentially what we're going to do on each of the routers. We're going to go into router 1, router 2, and router 3, and we are going to configure these devices. Interface tunnel 0, and we're going to say no tunnel destination. I think we should be able to get away with that without putting in the whole command. All right. Oh, dang it. Yeah, it said I can't make it multi-point because I have a tunnel destination specified. I would have had to make it remove the tunnel destination first, and then I could apply the tunnel mode command. So let's do that now. Tunnel mode, GRE multi-point, and right now we should be able to get that in there just fine. Oops, I forgot my tunnel interface. Try this one more time. Config T, interface tunnel 0, tunnel mode, GRE multi-point, and write and send. All right, so only one change in our topology has allowed us to convert from DMVPN Phase 1 to DMVPN Phase 2. All right, we've already specified the next hop server. The hub already knows the underlay and overlay addresses because that was already resolved. The only difference is we're just specifying point to multi-point or a multi-point GRE interface. This is actually the default config that you're going to see in the documentation from Cisco is DMVPN Phase 2, where we have a tunnel mode, GRE multi-point, and a tunnel source. All right, if I do a show DMVPN, I can see the tunnel still active. On router 5, do show DMVPN. We can see that we still have our tunnels active to each of the spokes. All right, so one minor change. What does this do for the topology? Do we still have adjacencies on router 5? Show IP OSPF neighbor. Yes, we do still have adjacencies. The adjacencies are formed over the tunnel interfaces. I guess the question now is, what is the impact, or how is this going to affect routing? All right. Now, if I do a show IP route on this hub router, I can see that I'm learning the prefixes. There's the one from spoke 2. There's the prefix from spoke number 1. And there's the prefix from spoke number 3. So we are learning about all the destination prefixes. Notice the next hop attribute is the actual spoke router. Now if I go to a spoke, show IP route OSPF, because we don't have let me get rid of the default routing. We would not want the summarization, the default summarization in this case, because ultimately I want to be able to resolve destinations based on the best path, right? I could do a trace route to 192.168.20.1, and the trace works just fine because I've got a default route to the hub. The hub then in turn has a route over to spoke number 2, or in this case, spoke number 2 over the tunnel. So we're going up to 10.5 first and then going to 10.2. But we're running DMVPN Phase 2, which means that traditional hub and spoke routing at the data plane is not very efficient. We'd like to be able to do spoke-to-spoke routing. So in order for us to be able to facilitate spoke-to-spoke routing, because there is no NHRP redirect, I have to suppress that default route from being sent out so that we can learn the prefixes as they exist on each of the spokes. no default information originate always. And if I now come into router number 1, I should see that we should start learning prefixes. Let's see if we're getting information in our database. We are. So we are getting our type 1 LSAs, our intra-area LSAs, but, yeah, go ahead.
You have the distribute list on there, right?
Oh yeah, I do have a distribute list on router 1. Thank you, appreciate that. Show run interface, or show run section OSPF, thank you. There is one thing I do want to point out though. This is not going to work very well, and I'll show you why in a second. Let's get rid of our distribute list. Show IP route OSPF. All right, there we go. This is the issue, okay? If I do a trace to 192.168.20.1, it's still going through the hub, right? And that's really part of the issue with OSPF is the way that this next hop address is not preserved when it's being sent from the spoke. So we're advertising routes from the spokes. The control plane is being managed by the hub. Routes are being advertised by the hub, but the hub is also modifying the next hop attribute. So it's saying, hey, if I learned about this prefix from this spoke, go ahead and send your traffic to me. Really, I'd like to resolve directly to the other spoke. All right. Now, I'm trying to think if there's a way. Let's try and flap all of the tunnel interfaces. We make sure we're good here. Show run interface tunnel 0, and see if there is some additional reachability information that we get. Oops. Shut that one down. Same thing. And we'll shut this one down. These resetting GRE tunnels and DMVPN configurations can be a bit of a hassle because just shutting down the tunnel interfaces does not always result in reconvergence. So it depends on the platform and the iOS, but usually shutting down the tunnel and bringing it back up, as long as you follow the correct order of operations, should work just fine. So we want to make sure we bring up the hub first, and then we'll bring up the spokes. 1, 2, and 3. And let's do config T interface tunnel 0, no shut. All right. Show DMVPN. Show IP route. All right. So I just want to make sure we're still learning the routes and learning the destination prefixes. But you can see here from router 1's perspective, to get to 10.10.10.5 is okay. But to get to 192.168.30.1, I should really be sending my traffic to 10.10.10.3. All right, let me see if I'm learning anything about show IP route 192.168.30.0. So we are seeing that it's coming from tunnel 0, but we're still seeing a next hop of 10.10.10.5. All right, so this is a bit of a problem because we're running DMVPN Phase 2. This should allow for spoke-to-spoke communication. The problem in this particular case is that there is no DR-BDR election. We're running point-to-multipoint, okay? And without a DR-BDR election, there's no way for us to preserve the next hop information. In an OSPF design, in order to preserve next hop information, that information has to be propagated to the DR, and then the DR needs to repropagate that information over to the other routers in that multi-access network. That's the only way to preserve the next hop information. All right. So if we do try to do any kind of trace route or generate any traffic, it's just simply going to look like regular phase DMVPN phase 1 traffic. All right. So what we need to do now is we need to convert our network to broadcast, where we're going to trick the router into thinking that this is a broadcast network. All right. So if I go into interface tunnel 0 and I do IP OSPF network broadcast, all right, let's see what the implications are there. Do show IP OSPF interface tunnel 0. We can see that the network type is broadcast. Our timers changed to 10 and 40. So that should allow us to, well, actually it will not allow us to form an adjacency, and here's the reason why. Broadcast means that a DR-BDR election needs to take place. Unfortunately, in point-to-point, which is what the spokes are running, they don't believe that a DR-BDR election needs to take place. So if I do a show IP OSPF neighbor, you can see that there is no DR-BDR election that takes place here. Now, it does say that we were able to establish an adjacency, but there are going to be issues with that adjacency. There's going to be communication issues with that adjacency. All right? And there you go. That's what we see. We received a hello packet from 50.1 indicating a potential network type mismatch. Now, does that affect our overall tunnel operation? Let me try and ping to 20.1. Apparently it does, right? So we're able to form an adjacency, but we're not able to resolve the graph because we're getting invalid or incomplete link state information. So what I need to do is I need to convert all of the routers to the same network type. But then there's another implication that comes into play in this case. This is why you try to avoid using OSPF over DMVPN. Interface tunnel 0. IP OSPF network broadcast. Now, this might work. It depends. It depends on, the timing of everything. But it should allow us to at least form an adjacency, because now we're doing a DR-BDR election. Router 5 technically should become the DR in this network because it was already part of a broadcast domain, but it also happens to have the highest router ID. But we should get an adjacency. We're going through the process. All right, we should get an adjacency, and we should be able to establish that router 5 is the DR. Patience. We should see this on this router as well. There we go. So we got our adjacency on router 2. Show IP OSPF neighbor. And we have our full adjacency on router 3. And router 5 is acting as the DR. Which is great, because that's what we want. We want router 5 to be able to propagate all the control plane information. If I do a show IP route, I can see that the next hop values are preserved at the hub. And if I go to router 1 and I do a trace to 192.168.20.1, there we go. That's what I wanted to see. Initially, it went to .5, but you can see here that it's going to .2 directly. So spoke-to-spoke communication is now able to take place because we have the DR preserved the data plane information, because the DR is just simply acting as a pass-through for the control plane information. Does that make sense? So the next hop value is preserved, but only because router 5 became the DR. What happens if router 5 does not become the DR? Right? Maybe a spoke router becomes the DR, or for some reason, a spoke router decides, because we're in a wait period or whatnot, a spoke router decides to claim the role as the DR. before we maybe include the DMVPN configuration and so on. All right. This is an issue with OSPF. A lot of documentation states that the DR process is non-preemptive, but actually it can be preemptive. It just depends on the state. Right? So let's say that I do a clear IP OSPF process on this router here. All right? And I've gotten all my adjacencies. If I do a show IP OSPF neighbor, I can see that router 3 now has become the DR. Router 3 has become the DR. The problem that we have is if I go to router 3, show IP OSPF neighbor, it's only going to have a relationship with the hub because multicast spoke-to-spoke communication is not allowed. Only multicast encapsulation is allowed on the communication from the hub to the spoke. So we may have some reachability here, but we don't have full reachability here, and that's a problem. All right? So the multicast that's coming from, in this case, router 3, can't be heard by any of the other spokes, which means we're not going to have full conversions. We're not going to be able to resolve the graph. So we need to make sure that in order to prevent any of the spoke routers from becoming the DR in this particular design, we need to go in on those spoke routers and set the priority of those tunnel interfaces to 0. When we set a tunnel interface priority to 0, IP OSPF priority 0, it means that those interfaces or the, oh dang it, mistyped something. Config T, interface tunnel 0, IP OSPF priority 0 and right. Try that again. All right. That means, and we'll have to do a clear IP OSPF process. Yes. That didn't work. I was wondering if that would work. All right. We'll just want to kind of flap OSPF here. Oops. Clear IP OSPF process. All right. So we established a full adjacency with the hub. Now we've kind of finally reached the point where we've got full convergence. We know who the DR is going to be in this particular topology. If we had redundant DMVPN hubs, we could establish that one DMVPN router hub would be the primary DR, and then the other hub would be the BDR, and so on. Okay. You notice that as I did the trace, all right, the routing kind of acted strangely at first, right? From a traffic pattern perspective, that first trace I did resulted in the packet going to the hub first, and then to the spoke, and then we went from spoke to spoke after that. I don't want you to think that that was some sort of redirect option or that was normal behavior. That's not normally how it should behave, right? The trace from one spoke router to the other spoke router should always go directly between them. All right? So the first packet might be lost because we're doing some sort of NHRP resolution for the tunnel interface address to the NBMA address, but we should see the actual request. So let's do that. Let's do a packet capture here. And let's see if we can see that information. I'm probably going to have to go ahead and clear out on router 1. Interface tunnel 0. Shut that down. And clear IP OSPF process, yes. Because I want to see the packets that allow us to identify this resolution request that's taking place. So config T, interface tunnel 0, no shut. So I should see in the packet capture some sort of NHRP registration, there's a reply. All right, so we're seeing that we're getting OSPF adjacencies coming up and so on. All right, now because the adjacency is happening with the hub, and because we're doing our DBD exchange, our link state exchange with the hub, we didn't see any kind of NHRP resolution request because we're not trying to discover a tunnel interface to NBMA address mapping. All right, but if I come back to this router now and I do a trace to 192.168.20.1, what I should see is initially the traffic is going to go through the hub, but I should also see in here some sort of NHRP resolution request and a response. All right, so we can see that right here. The packet actually failed, time to live exceeded in transit, time to live exceeded in transit, and then we see our NHRP resolution request. This probably is related to some sort of packet size error, but it's okay. All right, so we're seeing in this particular case, there we go. Nope, mandatory part, that's what I'm looking for. We're seeing in this case that we're trying to resolve, remember I was doing a trace route to 192.168.20.1, which is spoke number 2. So this is the source, this is the destination. I know the source NBMA address, but I don't necessarily know the destination NBMA address. And that's what I'm trying to resolve in this particular case. All right, and we would see that in the follow-up packet, in the reply. And we should see in this case information about the destination NBMA address. Let me see. Destination, that's still part of the original request. Let me stop this capture. Let's see. It should be. We're getting some issues here. I think these issues here have to deal with fragmentation. I'm not sure. I thought we pretty much adjusted our values low enough, but there should be an indication in here that, I mean, we can definitely see the resolution taking place, right? And actually, this is the response. Notice the underlay IP addresses here. We're going from 241 to 245, and the response is 245 to 242. So what's happening is router 1 is requesting the address for router 2. Router 5 is then notifying router 2 that somebody wants to establish communication, and then that's when we're seeing the packets actually being routed. Let's see here. This should have the appropriate addresses for overlay and underlay. So there's the initial ping that went through. Make sure this is my ICMP packet. No, this is UDP. What's going on here? Let's see. That's a UDP packet. That's what we're seeing in this particular case. Is we're seeing that first trace route timeout because we're going through the process of this NHRP resolution request, and this is essentially, I wouldn't say it's necessarily the response, but it's router 5 notifying router 2 of router 1's reachability information. All right, then we should see beyond that our packets. Actually, we wouldn't in this case, right? That's the other confusing part. Remember where I did the capture. I was capturing this data at the link level on router 5, which means that after that initial discussion, that's why it was confusing. We're missing pieces of the puzzle here because I'm not seeing responses from router 2 or I'm not seeing the communication going from router 2 to router 1 from the resolution perspective because I'm doing the packet capture on the link level at router 5. So we would have to do multiple captures. Not really necessary to go through that process, but you guys get the idea, right? In DMVPN Phase 2, there isn't an NHRP redirect that comes from router 5. We didn't see that in the packet capture. There's just a resolution request. So router 1 is going to go to router 5 and say, hey, I want to send traffic directly to router 2. How do I do that? Router 5 then notifies router 2, and eventually both router 1 and router 2 would resolve the NBMA addresses to the tunnel interfaces, which would allow them to communicate directly. All right? I suppose we could do a capture on router 2's interface. Let's try that real quick. We're almost done anyway, so kind of want to show you a couple more things here. We're still going to take a look at something that we would have to consider with regard to EIGRP, and then we'll also take a look at something we would have to consider with BGP. Okay, so let's go back to router 1. Interface tunnel 0. Shut that guy down. No IP OSPF or clear IP OSPF process, which I really shouldn't have to do, but since we lost our adjacency anyway, but I'll do it anyway just to be safe. And we'll do no shut on the tunnel interface. And I'm going to do a ping to 192.168.20.1. Now we know initially router 1 is going to send an NHRP request to router 5, but now we're capturing just the information that's coming from router 2's perspective. And I'd like to see what that looks like from router 2's perspective, if it actually did the capture. Let's see right here. All right. So let's see if we see anything in relation to NHRP in this particular case. Let's see, 10.2, so there's the OSPF. Hello. Are we seeing any communication to router 1? Nope, here's the pings. All right, so we're not actually seeing any NHRP messages going from router 2 to router 1. In fact, the very first communication that we see from router 2 to router 1 is just a reply to the ping. All right, that's because the NHRP hub proactively notified router 2 how to reach router 1. So the hub knew that the traffic was going to be sent to that traffic was going to be sent to router 2 from router 1. So it sent in that that message. Now we should have captured that NHRP information if it was going to router 2, but for some reason I don't see it here. You know what? We didn't see it. We didn't see it because it already took place. We didn't reset router 2's tunnel interface. So the resolution was already cached and we didn't have to get, well, actually here it is right here. I misspoke. So this is the actual resolution request from router 5. Router 5 to router 2. Now if I open this up, I should see in here that router 5 is notifying router 2 of information about router 1. Yep, there we go. So 241, the source protocol, the overlay VPN address is 10.10.10.1. The NBMA address is 241. Okay. So that's, but we saw that piece anyway. That was what we saw on router 5. We're not seeing anything from router 1 to router 2 though, because we're just replying to the echo request and echo reply using our NBMA address, or loopback interface, excuse me. Does that make sense? I mean, if you really think about this, this is kind of like a proxy ARP. The ultimate goal, of course, is to make sure that the data plane doesn't have to go through the hub for resolution. All right. With OSPF and DMVPN Phase 2, just to reiterate, we have to have some sort of broadcast. Well, I wouldn't say broadcast. We have to have some sort of multi-access topology. Could be either broadcast or non-broadcast, but it can't be point to anything, point to point or point to multi-point. Would have to be some sort of broadcast or multi-access network in order to facilitate this configuration. The hub needs to be the DR. The spokes need to have a priority of 0, and so on. We would have the option, potentially, of doing like an IP OSPF MTU ignore command, but in a real design, we wouldn't do that because if you flood the link state information and the packet is too large, larger than what you can accept anyway, then you're not going to be able to accept that packet and you're not going to be able to build your SPT, right? Also keep in mind that if a route to the tunnel points to the tunnel interface, it's going to fail because you have that recursive, continuous recursive lookup, and things will break in that particular case. All right. There was something that I wanted to show you about BGP. Oh, I got to change my batteries. Hold on. So let's say that we want to now implement BGP with this topology. Let's go ahead and remove our OSPF configuration. And we're now going to use BGP as our overlay protocol. All right. So let's go into config T. No router OSPF1. And let's just leave it at that for now. Take out OSPF. All right. So we'll talk about EIGRP and all the other stuff a little bit later on. But when it comes to BGP, we already talked about OSPF and all the complications that OSPF has. We still got some OSPF specific configurations on the interfaces, but we don't need to take that off. So in the case of where you have a really complicated design, where you need to be able to manipulate routes, BGP is really your best choice. In a smaller DMVPN design, EIGRP is probably your best option. But when you have a much larger design, much more complex design, even if it's DMVPN Phase 2 or Phase 3, BGP is typically what you'd want to have in that case. And there's a couple of ways you can implement BGP over the topology. You can create eBGP peering relationships between the spokes and the hub, and using private ASs in the overlay, or you can have one AS everywhere and the hub would be essentially configured as a route reflector for the BGP peers. Remember, we're trying to preserve next hop information. So a lot of times when we have multiple BGP peers and you want to use preserve next hop information, a route reflector is probably the best option. The only disadvantage of using BGP is that you have to manually update all your BGP neighbors, right? There's actually a way around this behavior, and this is what I wanted to show you. It was actually part of a different lesson, but I'll show you it here as well. All right. If you go look at the configuration guide for 15.3 and you look at routing under BGP, you can see that you have an option of creating BGP dynamic neighbors, and we're going to go ahead and set that up in this particular case. What we use is we use something called BGP listen. So I configure BGP listen on the hub, and then someone can send me a peering request by initiating that session with a TCP SYN request. That way, because all the spokes are essentially going to have the same configuration, we're now templating out our routing configuration along with our DMVPN configuration for the spoke routers. So we have a range of addresses that we would listen on and they're going to be running the requirements of the group, and then they should be able to form, as long as the requirements of the group are met, we should be able to form a BGP peering relationship on those between those peers. Okay, so we're going to run BGP autonomous system number 1 in this case. I'm going to configure the hub separately, and then I'll just configure all the spokes as a group because they're going to have essentially the same configuration. So we go router BGP 1. We're going to do an iBGP peering relationship here as opposed to eBGP. And then we're going to specify a listen range and create something called a peer group. So BGP listen range, and we're going to say 10.10.10.0/24 because we're going to be getting TCP SYN requests over the tunnel interface. And we're going to then associate those peers with our our peer group DMVPN. Okay, meaning that now we can take all of the properties of these neighbor relationships and create a peer group, specify the remote AS, specify all the other options or the properties of the group, and then we can configure essentially the DMVPN relationship. I mean the BGP relationships. So let's go ahead and say neighbor DMVPN, and we're going to say that's our peer group, and then we're going to say neighbor DMVPN remote AS 1. All right. We can do other attributes if we want to manipulate other attributes, but those are really the two main attributes that we need for the peer group. So if I do a show run section BGP, I can see the peer group configuration under BGP. All right. Now the rest of this I can simply do in Notepad. So let's go ahead and open up Notepad because we're going to go ahead and paste this configuration in the rest of our spoke routers. So route map loopback, those are the interfaces that we're using. Those are the interfaces that we're using to establish our adjacency and also the networks that we're going to be advertising. Match interface. Actually, we're going to use our overlay VPN for the adjacency, but we still need to create this route map because we're going to have to put in our network statements eventually. Okay, and then we're going to go into router BGP 1, and I forgot to make this guy a route reflector. I need to make the hub a route reflector. So let's do neighbor route reflector clients. Neighbor DMVPN route reflector client. There we go. All right. Now let's go back to our Notepad. And we can finish up our configuration here. We'll do a redistribute connected. Loop back. All right, redistribute connected loop back. So that's going to allow us to insert or inject the routes from the spokes into the DMVPN network. We probably would still have to add the local loop back from the hub. And then we're going to apply this configuration on all the spokes and the hub. All right, this particular part of the configuration. Now we do need to specify the peering relationship on the spokes. So in addition to doing this on all of the routers, so let's go ahead and apply that on all of our routers, we're going to have to also do apply a configuration on the spokes individually. All right. I didn't mean redistribute connected. I forgot my route map statement. Let me try that again. Route map.
The BGP log neighbor changes?
That's on by default. We could do that. We could apply that to the DMVPN group. let me go back to here and go.
Permit statement. The route map permit 10 or something.
Oh, what's the purpose of it? Is that what you're saying?
No, you have to permit, route map permit. You have to put a permit in the end of the route map.
No, you don't need a permit because all we're doing is we're matching. It's going to do permit automatically, right?
Oh,
Yeah, it's going to do a permit. It's going to do a sequence number automatically, but I keep forgetting to reference the route map in my statement here. So we'll try this one more time and send that over. Now we should get it through. So if I do a show route map, I'm pretty sure it's going to default show route map. Yeah, so it automatically defaults to permit in sequence 10. If I were to add additional clauses, I'd have to have, if I wanted to manipulate them, whether they're deny or permit, I would have to specify permit or deny. But you don't actually technically need it for one clause here. Okay.
okay.
Let's see here. The last thing I need to do, of course, is I need to tell the spokes how to get to the hub, right? So that's the next part of this configuration, which is on the spokes, we're going to go into router BGP 1, and we're going to say neighbor 10.10.10.5 remote AS 1. All right, and right. And we'll do our config T here as well. But you can see essentially this entire config is templated out. The only difference is on the spokes, we're actually specifying a static neighbor rather than just using the TCP listen or the BGP listen option. So let's go to R1.
Yes, Scott, I have a question.
Yes, sir.
I'm looking at JMD's configs, and they have a neighbor, and then they have the one of the spokes or whatever, and then it says inherit peer session, and then they name it. But what is the peer session that they're inheriting, or what is that command for?
I'm not sure. I'd have to look at it. I haven't used that option before. I'd have to take a look at that. It's not necessary.
What you're doing, they're specifying neighbors, and then doing this inherit peer session command instead. Okay, I was just curious.
You mean on the hub? On the hub or on the spokes?
On the spokes.
Yeah, it's not necessary. That may be for another function. I'm not really familiar with that, so I'd have to take a look at it. But yeah, this is the way that I've always done it. Just specify the neighbor, because the hub is listening for the TCP send requests for BGP, and it's going to automatically form the adjacency based on that.
Your way looks a lot easier and less complex.
It is very simple.
So I'm wondering, they over-engineered this.
Now if we go to our hub, show IP BGP summary, we can see that we have 3 neighbors, 10.1, 10.2, 10.3, dynamically created based on a listen range, and our listen range is 10.10.10.0/24. We're getting one prefix from each of the spokes, which makes sense. So we're learning our prefixes based on the redistribution that we did and the route map that's applied. So everything, has been learned specifically. Now, the nice thing about BGP, specifically IBGP, if I do a show IP route, 192.168.20.0, we can see that the route descriptor block describes who the route was learned from, and it also describes the next hop. So if I go to router 1 and I do a show IP route 192.168.20.0, I can see that this is the next hop address for that destination, but this is who described that route to me. So we're preserving the next hop information because of the IBGP peering relationship, right? You know that if you go from like an EBGP, one EBGP peer to an IBGP peer, next hop information needs to be changed. But in the case of this configuration, because these are IBGP peers, we preserve that information. And because router 5 is configured as a route reflector. meaning we're telling the router to preserve the next hop value. The next hop value is not going to be the hub. It's going to be the whoever originated the route. All right. So the route reflector itself does not insert itself into the data plane path. It's a control plane function. It provides the control plane function out of band to send out updates, but it doesn't preserve. It preserves the next hop information. Obviously, you probably wouldn't want to do this in DMVPN Phase 1 because we would want the traffic to go through the hub. But in DMVPN Phase 1, we might just be doing default routing out to the hub anyway, if that makes sense. All right. It really doesn't matter from a data plane perspective in DMVPN 1, like version 1 or Phase 1, because we have point-to-point tunnels anyway, and so on. All right. We're going to go back to that. There was a whole nother lesson that I had prepared, and I can't even believe I skipped over it, but we'll probably see that again. We'll talk about some other concepts on Wednesday as well. I'll do that lesson, and then we'll do the Phase 3 lesson separately. Yeah, there's a bunch of information that I had actually documented that I wanted to show you guys, and I thought we had already done that. So we have a little bit left here. Just a couple more things I want to talk about before we wrap up this lesson. And that is what happens if we're going to run EIGRP over the network. Right? Remember, we can't do any summarization from the hub to the spokes, and the next hop always has to be preserved when it's reflected from the hub down to the spokes. On the hub, we need the command, for example, no IP next hop self EIGRP X if we want to preserve the next hop value. And we're going to set this up and configure this in a minute here, and I'll show you what I'm talking about. That command actually works pretty well. Works both in classic configuration mode and address family configuration mode. But the only difference in AF mode is that you're going to apply it to the AF interface as opposed to maybe applying it directly on the tunnel interface. All right. Remember, it's always about preserving and reflecting down to the spokes from the hub the next hop information. All right. If I didn't do that, then the data plane traffic would traverse the hub, and we might as well be running DMVPN Phase 1 at that point. All right. In Phase 3, DMVPN Phase 3, the design is much, much simpler because NHRP solves the problem using NHRP redirects, and we don't have to worry about whether or not the next hop value is preserved. All right. So let's go ahead and let's do a quick show IP protocols here. I just want to check one thing real quick. We should be okay just doing an overlay, but yep. So we're running BGP 1. If I do a show IP route, yeah, we've got an AD of 200. eBGP would be AD of 20, but we're running 200 here. So we can just kind of jump or throw EIGRP in on the top here, and we don't have to remove BGP. So let's go ahead and do that. And we're just going to do a basic EIGRP configuration, router EIGRP1, and we're going to enable it on our overlay network, and we're going to enable it on our loopbacks. Okay. So we should now, in our routing table, see show IP route. Actually, let me do it on the hub first. We should see EIGRP routes and no more BGP routes for the spoke routers. We already know that there's going to be a problem on router 1 as far as learning routing information from the other spokes. So our BGP routes are taking effect here because of split horizon, right? Never advertise a network back out the same interface that you learn it on. So obviously, as one of the basic concepts of DMVPN Phase 2 is that we would want to go into the tunnel interface and say IP, no IP, split horizon. Don't confuse this one with this one. This one applies to RIP. This one applies to EIGRP. All right, so now if I go over to router 1, my BGP routes should be gone, and all I see are my EIGRP routes. But there's a problem. Next hop, right? If I do a show IP route 192.168.20.0, we can see that the next hop value was not preserved, 10.10.10.5, and the advertising router, the one that's helping me build the routing table, is router 5. That's the one that's advertising the network. All right. So there is another command that we need to run that would be configured on our hub router. Config T interface tunnel 0. No IP next hop self EIGRP 1. So now what we're telling router 5 is, hey, you can give people the route, but you need to tell them how the data plane is going to function. All right. I'm basically, this is what we call third-party next hop. I'm essentially telling you about how the routing, what network prefixes are reachable, but I am not modifying the data plane reachability. So now if I do a show IP route, we can see here that the next hop is preserved for the route 10.10.10.2. We're learning about the route from 10.10.10.5, but the next hop is 10.10.10.2. Okay, so if I do a trace route 192.168.20.1, it goes directly to router 2. If I take out the no IP next hop command, we should see that it now is routing through router 5. Very, very simple concept, not difficult to deal with. RIP, we don't have to worry about this because we're not performing adjacencies in RIP anyway. But with EIGRP, this is a big deal. We need to preserve the next hop attribute in DMVPN Phase 2. If it was Phase 1, it wouldn't really matter because the traffic has to go through the hub anyway. All right. All right, guys. Well, that pretty much covers DMVPN Phase 2. We have actually part 2 of DMVPN Phase 1, which I thought we had done, so I will do that later. We'll go ahead and plan on doing the lesson on Wednesday. So it will be a little bit longer than I had thought originally because we've got to go back and do part 2 of DMVPN Phase 1, and then we'll do our DMVPN Phase 3 discussion, all right? So we'll see you guys in the next